So we're solving systems with graphing, and I'm just going to kind of go over a couple things real quick. So a system of equations is when you have the same number of variables as equations, or sorry, when you have the same number of variables as equations, you can use those equations to find another variable. So for instance, if we had the equation 2x plus y is equal to 10, we can't solve that because there's two variables. It depends on what x is. You could change your y. If x is 5, y is just 0. If y is 10, then x is 0. So there's a lot of different things. You can't solve for x or y because you only have one equation with two variables. However, if that gave you a second equation with two variables, now we can solve. So as long as you have the same number of equations, variables, you can figure that out. So this is what we'll get into later, but also, or obviously, and 3x minus y plus 2z is equal. This one you won't be able to solve yet. We have two equations, but we have three variables. So if you want to solve with three variables, you need three equations. So that's what we'll get into. Okay. A solution. Now, again, I'm hoping all you guys are like, yes, we get it. We know what a solution is. But I feel like every year there's always a couple people that they know how to solve these, or I guess more than you think, where they know how to solve these, they know how to do these, they're really good at them, they're A students, but they still kind of just need a refresher in what it means to be a solution. So a solution is to the system is an ordered pair, and that's for our purposes. Obviously, kind of depends on the problems. But the big deal is the ordered pair that makes both of the equations true. That's the punchline with this. So the way I did this one real quick is I gave you two equations. The first equation, I listed out all the answers, or a lot of the answers. Now, technically, there's an infinite amount of answers to this. It could just keep going and going. Two numbers that add up to be 20. I mean, you could have x is 120 and y is negative 100. That would add up to 20. So there's an infinite amount of solutions, but I just made a list of a lot of these solutions. All of these add up to be 20. And again, they keep going and going and going. Then the other equation, I did the same thing where I listed these out. These are all ones that when you plug those in, you get 25. So these are all the answers. Again, etc. It goes on and on and on forever. But as much as those two have an infinite amount of solutions, they go on forever and ever. As much as that works, you only have one solution that works for both of them, and that solution is that 515. But when I draw a line, when I'm graphing a line, that line represents every single one of the solutions that makes that equation true. So we'll draw two lines, one for each equation. Wherever they intersect is the one single point that works for both of them. So if you plug it into both equations, they give you 20 for the first one, 25 for the second one. That's what a solution is. That's what we're looking for. So there are three different types of way to solve these, or three types that we'll get into: graphing, substitution, elimination. For any system, you can use any equation or any type. So for instance, you could just use elimination for every single type. That's up to you. However, if you take the time to realize what you're looking for, a lot of times if you can do all three of them, you can choose the easiest one. Because there are times that it's really hard to use elimination, but graphing is actually pretty easy. So graphing is the one that I use if both of the equations are in slope-intercept form and the slopes are fractions. If both of your equations are in slope-intercept form, not that hard to use graphing. You can always use graph paper if you choose to do that. Substitution, we'll talk about this tomorrow, but substitution I use when one equation is solved for one of the variables. Obviously, if there's more equations, if both the equations are solved for a variable, that's great too, but at least one of them has to be solved. So in other words, one of the equations has a variable that's all by itself. And lastly, elimination is when both equations are in standard form. If both equations are in standard form, that's great. I'd use elimination. So just a quick note, obviously not every system will fall nicely into these three categories. Most of the time when a system doesn't fit into these categories, we can manipulate them and set them up as elimination. Not every time, but most of the time that's what's easiest for students. So I just put a punchline that not all equations ever will fall into these three categories. So usually if they don't fall into one of those categories, I recommend putting them in standard form and using elimination. Not every time, again, other times you might need something else, but usually elimination is ones that students are most familiar with, or at least they think that's what they're best at. So if you ever have a problem that doesn't fall into those categories, I would just use elimination. You'll have to do a little bit of legwork, but that usually works out better than the others. Okay, so now let's get into solving by graphing. So step one, get each equation in slope-intercept form. If you want to use standard form and use the x and y intercepts, you can. You're more than welcome to. I never do that, and the main reason is because I like to do the same thing every time, and so I just like to get it in slope-intercept form. I'm more familiar with it, but again, you certainly do not have to. Step two, you're just going to graph both those lines, and then wherever the lines intersect is your answer. It should always be an ordered pair. So, number one. Remember what I said earlier when I said there's an infinite amount of numbers that I could sub in for this, or there's an infinite amount of solutions that work for this? That's what this line is. So when I graph this, my line is up to -4. My slope, I always put the negative with the numerator, so it's down 1, 2, 3, 4 over 1, 2, 3. I personally recommend you don't have to do this, but I either use a straight edge to make sure it's exact, or I don't use a straight edge because I don't have one. I just do the slope a couple different times until it's off my graph, especially for the first one. So down 4 over 3 right is the same as up 1, 2, 3, 4 over 1, 2, 3 my left. 1, 2, 3, 4 over 2, 3. So here's the deal with this line before we move on. Just FYI, and do it quick because most of you guys don't care or need to know this. But remember when we had inequalities where we shaded where our answers are? That's essentially what it is. I for every solution that works for this, and in every one of these, even these decimal places, decimal that this line is, if you would sub it in for this, it would work out. So that's what it is. This line represents every single solution that does work for this. You can pick down here, even these decimals, that would work. Those would be solutions. And you don't really need to know that, but just FYI. Now the other, we're going to do the same thing. We're going to highlight all those. Do our line. So that's 6. I go up 1 over 1, 2, 3. Now again, if you don't use a straight edge and if you don't use your slope, if you draw your line a little bit crooked, you'll probably get the wrong answer. So I do my slope, and now the second line, I just do it until I have my answer. So going up and to the right is the same as down to the left. 1, 2, 3. 1, 2, 3. Again, I technically could do it another time, do that right here, but once I have my answer right where they overlap, then I'm done. Sometimes you have to do it once for that, sometimes you have to do it 10 times, it all depends. But now I know exactly where that ordered pair is. Pair, make sure you remember your x comes first. You have to move your ladder before you so you have to go left and right first. So that's -6. Then up to 4. -6, 4 is your solution for that. Moving on to the next one. X is equal to. I'm hoping there's a red flag. Even if you don't remember what it is, I'm hoping there's a red flag that you know, okay, well, that's either a horizontal line or a vertical line. If you have x and that's it, there's no other y, just x is equal to a number, that is going to be a vertical line. The reason I remember this, I mean, at a certain point, you just have to try to figure out how to make yourself memorize it, whatever you're going to remember. But the way I remember it is if it's an x, that means it has an x-intercept. If it has an x-intercept, it's going to be a vertical line. That's the best way to look at that. Then from here, graph this one. 1, 2 over 1, 2, 3. More times, but I have my answer already, so I'm going to stop. An answer is here. That is over down 1. Now, this with this one, I'm not going to get into this a ton, but I know my x is 3 for this answer because this one tells me x is equal to 3. So that's how I know that x value has to be 3. I don't actually have to know that, but we're quick. And number 3, -5 is my y-intercept. I go up 1, 2, 3 over 1. Again, since it's my first line, I just do that slope a bunch of times. It's not hard. Up 3 over 1, up 3 over 1, up 3 over 1, down 3 over 1. That way my line doesn't have to be perfectly straight, but you'll be able to see what your answer is. Now my next one's not in slope-intercept form. So to get in slope-intercept form, I need to divide everything by 3. So I have y is equal to 2 over 3x. 6 over 3 is 2. So positive 2. I go up 1, 2 over 1, 2, 3. Again, do that a couple times if you need to, but I don't need to. I just hit my other line, so that's going to be my answer. Not to beat a dead horse, but if you look at my answer, if you don't look at the points, if you just look where my lines cross, it doesn't work very well. It's not crossing where it needs to be. That's why I put those points, and that's why I don't use a straight edge. I just use my ordered pairs. But again, either way, either use a straight edge or make sure you're doing your slope. That answer is over 3 up 4. Go ahead, do those next 3 on your own, and then we'll move on to the portion of this. All right, those are my 3 answers for those. Don't make this harder than it is. It's graphing. But also, one of the common mistakes, people go a little bit too just a little thing. So make sure you're paying attention. Pay attention to positives and negatives. Pay attention to make sure the first number is your x, the left and right number. The second number is your y. I've had people flip that around. Your y-intercept, make sure that's on the y-axis. I have a lot of people that have still put it on the x-axis. Any questions on those? All right, moving on. So we're going to do some of these special cases. Talked about this a lot for some of these other problems. So there's 3 separate outcomes. And I will say out of these 3 outcomes, really only 2 are special cases. So there's 3 outcomes. The 3 outcomes are you either have one solution, no solution, or infinite many solutions. So one solution is what we normally get. So every problem we just did, we get one solution. I've asked questions on tests before where it says, how many solutions does the following have? And students get really confused because they just solve and they don't know what to do. It's one solution. Every other problem, I mean, again, if you have 2 straight lines, there's only one way that they can both intersect each other. They can't intersect each other twice. So normally, every problem we do, or most problems you do, it's one solution. You end up getting one solution, one ordered pair. For number 4, this was our one solution. Number 5, this was our one. Number 6, this was our one. So that's what we normally get, one solution. So the special ones are no solutions and infinite many solutions. Now again, think of it this way. We're trying to figure out where the lines intersect. So if they never intersect, then there is no solution. So if the lines never intersect, that means there is no solution. Now, one way to look is this means they will have the same slope. We talked about that earlier. I forget chapter 1 or 2. But when the lines are parallel, that means the lines have the exact same slope. Perpendicular is opposite reciprocal. We don't have to deal with that right now because perpendicular just means they intersect once. That's the first case. So parallel, they never intersect. They will have the same slope, but different y-intercepts. You always want to make sure you double check that. And the reason is because the other outcome is infinitely many solutions. So what that means is you have two lines on top of each other, aka they're the exact same lines. So when you graph both your lines, they end up being the exact same line. That means it's infinite many solutions, which obviously you can assume if they're the exact same line, they have the same slope and the same y-intercept. And that's why I specified with no solution that there are different y-intercepts. Now here's the deal with the infinitely many solutions. We've talked about we talked about all real numbers being a solution. Technically, that's not the answer I'm looking for this. Now, honestly, if you put all real numbers, I'll probably give you credit because I get where you're coming from. But technically, it's not all real numbers because infinitely many solutions of all real numbers aren't the same. All real numbers, no matter what number you pick, to give you a solution. They give you 10, 15, 34, negative 8, pi, square root of 2. Doesn't matter. Whatever number you pick, every single number, all numbers will work to get you a solution. I mean, not all numbers are going to work, but you have an infinite many that do. We'll get some examples of this in a second. But you can have 2, 3 works, 4, 6 works, 8, 12 works, and there's an infinite many solutions that do work. But negative 1, 3 doesn't work. Negative 4, 10 doesn't work. So there's also a lot of answers that don't work. But again, there's an infinite amount that do work. So one solution is what we normally get. No solution is a parallel. Infinitely many solutions is the same line. So really quickly, if you haven't already, go ahead and do number 7, 8, and 9. I'll put the answers up here in a second. Make sure you are graphing these. I know some people will notice if they have the same slope or if they're the same line. But please graph these and see what they look like. I'll give you a little bit, and then I'll walk through these with you. All right, real quick, I'm going to go over the answers. Number 7, they should be no parallel. Hopefully realize, I know sometimes I mess it up, but normally if I make it and they don't intersect on the graph, obviously you can see they're going to intersect somewhere. These are two parallel lines. You cannot foresee them intersecting. But if you can't tell they're parallel, again, you look, they've got the same slope. So this is no solution. They will never intersect. There's no two ordered pairs you can put in there that will work for both of them. Again, there's a lot of them you'll put in for the blue line that'll work. There's a lot of them you put in the red line for work, but there's none that work for both of them, and that's the solution we're looking for. Number 8 has one solution. It intersects once. That solution is -1, -1. Number 9, I did not finish this one because I want to make sure you see this. I solved this first one and got this 2x minus 2, so I graphed that one. And now when you graph this one, my y-intercept is 2. My slope is up to over 1. You end up with the same line. You guys hopefully realize that just by looking when you got the answer, how those two lines match. But I wanted to make sure you saw the concept of technically, people would say they're two different lines. They just end up being the same equation when you simplify. So right on top of each other, that's infinitely many solutions. I abbreviate that down to the infinity sign. And I either say infinitely many sol or infinitely many or infinitely. I can usually piece those together. Move on, 2 things. First off, this is going to show up with every problem that we do or every lesson that we do. So when we do substitution tomorrow, there's going to be special solutions, special cases. When we do elimination on Thursday, these are not that hard. people forget these. A lot of people, since it's an answer that they don't get a lot, they kind of panic, then they try to figure out what they did wrong, and then they end up making up an answer or guessing. Make sure you go slow. If this happens, check your work. I always want you to check your work. But those are your three options. So the next thing we're going to look at is these systems, their inequalities. So we're just doing shading. So I thought about doing this in a separate day, doing this solving stuff first, then doing inequalities later. But really the thing is, it's all graphing lines. If you can graph lines, you can do all these. So we're going to do the same thing as we did before when we did normal inequalities. Again, just like we're talking about with the other things, we're going to do both of them on the same graph. Wherever they wherever they overlap is going to be your answer. Now, if you pay attention to this, I will give you some hints. You don't have to do it this way, but some things I think help students stay organized when I get to the shading part. So we'll talk about that in a second. So I'm going to do the first one. So the first one's 2 is y-intercept. I go up 1 over 2, up 1 over 2, up 1 over 2. Actually, we just did a chapter or two ago. It is a solid line because it's got that line under it. Then we shade below this intercept form below. I think it should be a little bit easier. So moving on to the next. Is negative 3. I go down 2 over 1 to the right, which means up 2 over 1 to the left, up 2 over 1 to the left. This is a dotted line below. So this one I shade here. Now, a couple things with this, and again, I'm going to spend on talking about how you make this look not like a nightmare. So first off, if you have this on your paper, I can figure it out. You did all the lines I did are horizontal and vertical, and so I can kind of see where it's checkered, where they overlap. So as long as I can tell where they overlap, or if you put a little arrow or something, that's good enough. But first off, that means these are our answers. Or are these solutions. So again, remember what we talked about with shading. All these solutions over here that we shaded with blue, that worked for the second one. That makes that one true. All these that work over here in the red that are shaded work for the red one. We want them to work for both of them. That make both of them true. So that's right here in the middle where they overlap. That will make the bottom one true and the top one true. So that's what we're looking at. We're looking for where they overlap. There's two ways that I like to do it. Obviously, you don't have to erase. Here's is I graph this one like before, but instead of actually some little arrows, okay, this one's shaded below. Today is actually labeling up here below. Below. Graph that one down to up to over 1. That is the dotted line. Also shaded below. So I draw these which way I'm shading. And the other way I start doing it. So if I'm going below the red one and below the blue one, where's the overlap? Where's it below both of them? That's that section over here. You don't have to do it this way, but this is a lot more clean because all I'm doing is shading my answer. All the blue shading is below the blue, all the red shading is below the red, so the place where the overlap is right here in this little triangle area. You don't have to do it that way. I know some people, they don't draw these little arrows and say below and below, so they kind of know where that's at. I don't care how you graph it, as long as I can tell where your final overlap is, I'll give it to you. But I'll be honest, I've done this before, and I have no idea where the overlap is. So whatever you need to do, if you want to be an artist and make it look super good, you can, or you can just draw a little arrow. I don't care. Like I said, I'm not nitpicky, but I do need to see where they overlap. All that said, after talking about that for 35 minutes, that's it. There's really not much to it. That's I was talking about ways to shade. Be careful. You might want to double check this. That rule still says that if you ever divide by negative, you have to flip your sign. So I end up getting equal to negative 5 over 2 x minus 2. 1, 2, 3, 4, 5 over 2. Over 2 to the left. That's the following. Says y is left shade below this one. Don't have to do it that way, but I think that's the best. I think it's the easiest, I should say. The next one, my y-intercept is 2. I go down 1 over 2, down 1 over 2, up 1 over 2, up 1 over 2. There's a dotted line. And you also shade below. So where are they shaded? Both of them? And that is below the blue, but it's also below the red. Over here is below the red, not below the blue. Up here is below the blue, not below the red. That green shading is the only place they're both. Number 12. We start off with a vertical line. Now, again, there's really not an above or below, but if you want to think of it then as left and right, you can, just like we did before. If x is less than, we shade to the left. If x is greater than, we shade to the right. And my last one, my y-intercept is 2. I go up 1, 2, 3, 4, 5 over 3. 1, 2, 3, 4, 5 over 3. This one's a dotted line. And this one you also shade below. I didn't mean for it to be like this, but apparently all these you shaded below, but that's okay. So below the blue and below the red, you're right here. Again, everything over here is below the red, not the blue. Everything over here is the blue, not the red. It's only this small sliver that's the solution for both of them. I'm going to skip this you do part really quick because I want to go on to the last thing, number 16, because I think this is very important. So number 16, and my graph looks a little bit better than yours because it's in color. So if you want to pay attention to that, you can. But circle the ordered pairs that are solutions. So there's two ways to do this. You could sub them into the equation. So sub them into both equations and see which one. X and Y for the first one. 2 for x and 5 for y. I get 5 is greater than or equal to 1/2 2 plus 1. So 5 is greater than or equal to 1/2 times 2 is 1. 5 is greater than or equal to 2. That is true. I have to try the second one. Plug in 2 and 5. 5 is less than or equal to -2 times 2 minus 4. 5 is less than or equal to -4 minus 4. 5 is less than or equal to -8. That is not a solution. So this one is not the solution. Through and plug all your equations in, you can. It just takes a while. If you're looking at the graph, though, you have to be careful. First off, let's make sure we know what this graph means. So the blue line is blue, and red, and up here you can kind of see where it's blue and red is where they overlap. That's the final solution. That's the solution we're looking for. We have an ordered pair in here. That's the solution. If it's anywhere else, it's not a solution. However, make sure you know the dotted, the blue line is solid. That's going to come into play here in a second. If not, I need to make some changes. So if you have the graph, all you can do is put those ordered pairs in there. So 2, 5 is, let's see if I can zoom in. 2, 5 is over 2, up 1, 2, 3, 4, 5. So that ordered pair works for the blue one, but not the red one. And that's what we just found. It worked for one of them and not the other. So that's not our solution. What about negative 5, 0? So negative 5, 0 is 1, 2, 3, 4, 5. Negative 5, 0 is right here. It's where the blue is shaded and the red is shaded. So that one works for both of them. Negative 2, negative 5 down here. Whoops, right here instead, rather. Again, that one doesn't work because it does work for the red one, but not the blue one. Now, here's where it's going to start getting tricky. I hope. Negative 4, 4 is right on the line. If it is right on the line, it depends on if it's a solid line or a dotted line, because that's what that means. A dotted line means everything below that red line works, but if it's on the red line, it's not true. I'm not going to but it's that underline or not underlined. If it's not underlined, equal to doesn't work. So if you plug anything that was on this dotted line, you get 5 is less than 5. It's not less than, it's not it's equal to, not less than, or 10 is less than 10. So the punchline, if you have a point that's on a dotted line, that means that point does work for the blue line. It's in the blue shaded, but it's not on the red shaded because it's a dotted line. So that one doesn't work. Negative 4, negative 1. This one is on the solid line, and it's in the red shaded area. So that one does work. It works for the blue one, and it works for the red one. Negative 2, 0, right where they intersect, does not work. Remember, it's got to work for both of them. And it is in the blue shaded. It's on the blue line, which is solid, so that one works. But it's also on the red line that's not solid, so it doesn't work for the red line. So it works for the blue, but not the red. So it's not a solution. And I don't have it on here, but last and not least, what if you had one over here that was on the solid blue line? Well, because we said if it's on a solid blue line, it is a solution. Well, it's only a solution to the blue line. It's not in the red shaded region, so that all of a sudden is not an answer. That's not a solution. You will have a couple questions like that on a test or a quiz, mainly because I really work, but you kind of have to make sure you're thinking about things and make sure you're being aware. Any questions on that? Again, I know it's one of those that's a little bit confusing and it might take a second to click. But again, ultimately with that one, you're trying to graph. It's got to be true. It's got to work for both of them. So when you look at the shaded area, you can always try to see, does it work for the blue one and the red one? And if it's right on the red line, that doesn't work for the red one because it's dotted. All right, so you do have your worksheet. The exit ticket should be up there, or the homework check. If you have any questions, let me know.